Today our speaker, Charlie Miller, is actually a principal engineer at Accuvant Labs and holds a PhD from Notre Dame. And the topic today, battery firmware hacking. So please join me in welcoming Charlie Miller.
Thanks. Thanks for coming. Thanks for having me. I don't know about you, but I'm thinking about bailing early and seeing Steph and Esther's talk. So if we all want to do that after like 5 minutes, it's cool with me. But what I'm here to talk about is a little experiment I did with battery firmware hacking. All right, so about me, so that was a good introduction, but a little more. I used to work at the NSA. I was doing a bunch of mobile stuff, so I was the first to have iPhone and Android hacks. I won this beautiful jacket at Pwn this year. I won a few other things. I've written a couple books, and I have like various degrees and stuff. So that's me. Oh, and of course, the most important thing is there's a InfoSuck comic that has my name in it. Although I don't really get it, but I don't know. Maybe it's because it's about me. Okay, so why did I get into this whole battery firmware stuff? So last year I came, and I give talks here a lot, but it's usually about some totally obscure part of OS X, or like in the greatest of all worlds, I can pop a calc on your Windows box or something, right? So I saw Barnaby Jack's talk about ATMs. I was like, that's really cool that that's something that you can just explain to your grandma or something, like, hey, that ATM, I can make money come out of it. And so I was like, I want to work on something that I could explain easily to somebody. So I thought for a long time, and then I came across this video on you can look it up on YouTube, and it's these guys, they tampered with the battery, of course, but they made the battery, this lithium-ion battery in their computer explode, and it's like, the video is crazy. The fire's just like, it's like off the screen and right where your hands would be, and I was like, wow, that's really cool. I wonder if a remote attacker could do that to a computer. So that was what I set out to do, was see if a remote attacker could get into your computer and make this happen. So the spoiler is I didn't do that. I didn't succeed in doing that, despite what you may have read in some of the blogs about my talk. So what happened? Well, you'll see. I think it's still an interesting talk, and I'll tell you all about what I did. What I managed to do was what you'll see is basically take over the battery and make it do whatever I want. But it's not like there's a button you push and it makes the battery blow up. If there was, I probably would have done it. But it's like there's like thousands of these parameters that you can adjust, and they all have different effects. And you have to charge it and maybe charge it a bunch of times. And I sort of didn't. And I work out of my house, so I didn't really want to have the thing blow up in my house. There was one time I was driving down the road, and I saw like fire trucks going the other way, and I was like, oh shit. And so I called my wife. I was like, hey. Well, first she answered. That was good. And then I said, go upstairs, and there's a computer in my in my office. Unplug it. So So anyway, it's a worrisome thing. But anyway, so I didn't. The spoilers. I didn't blow up anything, but I did do some pretty cool stuff. So this is what it's about. So what am I going to talk about? So basically, how smart batteries work in laptops, and then basically my story of I'm a software guy, so I didn't know much about hardware. I still don't know that much about hardware. So basically, like the story of me trying to figure out how this works and how I can change it and make things. And then at the end, I'll talk about like, so what, right? So I can change the battery. What's the effect of that? And that's the part I don't know so much about because, like I said, I'm a software guy. But it's possible that you guys can continue this work. Someone who knows more about this. Okay, so so when I first started doing this, I had no idea how batteries work and laptops charge the batteries and stuff. And so this is a little bit. I didn't know this, but just so that you guys have an idea of where I'm going. There's this document called the Smart Battery Specification, and it describes how smart batteries work and how they're charged and the whole system. And so this is like motivation for why I decided to look at the chip that's on the battery. So it says, safety, of course, is the primary design goal of the smart battery system. And then it says, blah, blah, blah. It says the primary intelligence of the system is inside the battery pack. So that means that you can take any battery you want off the street and plug it into your laptop, and it should work. So I don't care if that battery, is lithium ion, if it's nuclear powered or whatever. The computer should be able to talk to the battery, and the battery will tell it what to do and how to charge it. And so the brains of the whole smart battery system is on the battery, and that's basically what I went after. And so, and if you keep reading, it says, so the reason that they did this is the battery is in a position to know the most about what's going on. So it knows exactly how much capacity it has. It knows how much, what it was designed to do. It knows what chemistry it has. It knows, exactly how to charge it and that sort of thing. And so the smart battery is the key to the whole charging system. Okay, so the smart batteries, if you pull one out, and I'll have some pictures in a bit about what it looks like. There's a little embedded controller on it, and it talks to the OS and the charger, and it says things like, so the computer, and when you turn on your computer, it says you have 87% charge or something, right? And the reason it knows that is because the operating system has asked the battery. It said, hey, how much charge do you have? And the battery says 87%. And some other, it's more complicated than that a little bit, but the idea is that it queries the battery. And like I already said, the battery there's lots of safety mechanisms built into the system, but the main safety is the battery's job to do. And like I say here, you can configure it for different systems. And this little picture I have here is on a MacBook. If you go under more information about your system, there's one you can click on power, and it tells you these are some of the things you can read from the battery. And this one is from this MacBook here, and it actually says the name of the chip. So if you look, it says device name BQ20Z451. That's the chip that is on the battery. The ones I was looking at didn't say that, so it didn't give me that hint. I had to figure it out. I'll show you how I figured it out. Okay, so what can happen? All right, this is sort of the, why do we care? Besides, it's just sort of technically interesting. Well, the one thing I can definitely do is brick a battery, because I did that so many times on accident. So you can definitely make someone's battery not work anymore. As far as the computer is concerned, there's nothing plugged in. It can't talk to it. It can't accept charge. It can't uncharge, and you can't fix it, as far as I know, without putting on a new chip or something. I'm going to show you later that I can reprogram the battery to report whatever I want to the charger and the operating system. So in theory, maybe you could trick it into having some problems. But again, there's layers of defense, and I'm not sure if you can. I definitely get through the first and biggest layer of safety, but I don't know if the other layers you can get through or not. Another thing you can think of is if you can put code onto the battery chip that's going to keep running, that's going to survive reinstallations of the OS, for example. So you can imagine an idea where the OS or the code in the battery is constantly attacking the OS. So maybe it just eats up all the, and I didn't do basically any of this except the bricking, which was an accident. So you can imagine eating all the bandwidth on the little SM bus wires, causing the OS not to work, and this is going to survive reinstallations. And then if there was a bug, and again, I didn't find such a bug, I didn't really look, the OS is parsing the values that the battery is giving it, so if there was a bug in that, you could imagine being able to attack from the battery into a clean installation of the operating system and implanting like malware or something. And then another thing that is sort of interesting is, so you have code running on this chip that's sort of not the main processor, and so you can see other things maybe going on, like communications to and from the TPM chip or something like that. So you sort of have an inside thing. And then another thing that is sort of interesting that I don't even have a slide for because it's so silly is that if your battery is starting to not work so well, you can make it look like you just bought it, and then you can take it into Apple, and they'll give you a new one. Okay, so this is the start of my story, and again, I know a lot about software and that sort of thing, but I don't know really that much about hardware. So this is why, normally the projects I work on are like a couple weeks or a month, and it took me like 7 months to work on this battery project. So what did I start with? Well, I had my computer, and I had a battery, and that was it, right? And that's not much for me since I like IDA Pro and stuff. So I did a Google search, battery firmware. And the first thing that comes up is apparently Apple released a firmware update in 2009. So I was like, oh, that's cool. This is software. So I'm going to download this and check it out. All right, so I reverse engineered the updater. And it basically boiled down to the communications to the battery. We're calling this function IO connect method structure is structure 0. So it's just a way to talk to a particular CACST or device driver. So that's the way that the firmware was talking to the battery. The firmware update was talking to the battery. So, and the particular driver it was talking to is called Apple Smart Battery Manager. So you can see like on the one on the bottom there, it's opening up the driver. Okay, so that was good to know. So I know what driver is important, and I sort of see how to talk to it. So I can see, again, looking around, I see that the source code for this component called Apple Smart Battery is available on the Apple site. So I download that. Actually, it's actually called Power Management. So you download that, and you get like a bunch of cool files. Like it doesn't build, and because it's missing some stuff, they don't want you like messing with it. I guess I don't know why they even released it. But the good thing is they have some header files that have some good stuff. So you can see this, little excerpt from this header file talks about different things. And I actually wasn't smart enough to realize it yet. But this thing that says SM bus host to Smart Battery Manager, like that's really important. This is like the whole thing about smart batteries and how they communicate. Okay, so back to the firmware updater. So I reverse engineered it, and at this point I had seen from that header file what certain values were supposed to do. And so I could see what it was up to. And so it would do things like it would read the device name from the battery. It'd say, hey, what's your device name? The battery would tell it. And it would compare it to a list of ones that it was allowed to update. And it's like, OK. And then it would ask for things like your firmware version, your pack number. And again, it was just like, is this OK? Is this OK? Is this OK? And then finally, it started to do something. And then there's some things that weren't in the header file. So it was doing something I didn't know. But basically, you would see things like the code like this where, so I saw from the header file that the value 21 hex was to get the device name. And so it would just move that in the EX and would call this function that was a wrapper for that other API function I talked about before. OK, so it's fine and dandy. And then once it passed all the checks, it had this code. And this was a little strange. So it has these values. It's writing words to the battery now instead of reading. And it's like these unknown numbers, right? 414 and 3672. And so it's very different looking than the rest of the firmware updater. So I was like, what are those values? So, back to Google. I don't know what anyone ever did before, Google. So I type in that number into Google, and what do I see? I see things that say, like, this is the default. And then you see, like, you'll send the data 414 to address 0, which is exactly what I see. And immediately thereafter send 3672. Well, that's exactly what I see, too. So this is definitely something important. Like, it's what I'm seeing. And it says, this chip, BQ, something, going to unsealed state. So, OK. So it's got something to do, this is like a way to unseal the battery somehow. And so then again, just Googling that value some more, I come across this document on the Texas Instruments website. So it says, so I've learned that it's a Texas Instruments chip because I'm like way too scared to actually take apart a battery at this point in the story. So I've learned it's a Texas Instrument chip. That's cool. I've learned that Apple uses the default unseal key. So this is a key that allows you to make changes to the battery. So that's good. And then there's this other, so that's like the equivalent of a password to a user account in Windows or something, right? So you can, that's good as a starting place, but you can't, install software or something. Then there's this other key called the full access key, and that lets you do more stuff. And so there's a default value for that too. It's all Fs. And so I tried that, and that worked too. So Apple didn't change, either of these passwords. And so that's what allows me, that's basically, like, if I had to summarize the whole talk on Twitter, it's this slide. So they didn't change the passwords, which then is going to allow me to do a bunch of stuff. OK, so I still didn't know. I knew it was from Texas Instruments. I still didn't know exactly what chip it was. So I still wanted to only work in software. So what I did was there's a way that you can access data, flash data from the battery for different what they call subclasses. And so I wrote a script that would do that for every subclass, and each subclass would return a certain number of bytes. And each chip had for different subclasses, returned different number of bytes. And so I just did that, and then I had like a fingerprint for it, and then I just compared through all the documents to see which one matched. So it's it's really stupid to do it this way, but that's what I did. So So this is what I saw. So I read subclass ID 0, it returned 22 bytes. And I read subclass ID 1, it returned 25 bytes, and so on. So then I started, I just was going through the Texas Instruments site for all their chips data sets, and I wanted to find one that matched this. So this is the one. So you can see, first level safety is, the first data subclass ID. And it returns, there's 20 different values, and the 20th one is 2 bytes long, so it returns 22. And then the next one's called first level safety. So the first one was first level safety voltage, then first level safety current. And then you can see there's 25. And so I keep doing this, and then the next one is first level safety temperature, and so on. And so eventually I see that all these values match up exactly with what I saw. So now I was pretty sure what the chip was. It is Texas Instruments BQ20Z80. So that's what I think the chip is. Okay, so that was me being scared of software. But eventually, I was like, well, let's actually take a look at what's going on. So I ripped one apart. So this is what the battery, and I should say, those passwords, right, the unseal password and the full access password, those I've checked in every computer I could get my hands on, every Apple one. So this is like computers from 2007, MacBooks, MacBook Airs, MacBook Pros. So everyone I've ever checked has those default values, including like this brand new computer. So, but this particular, all my actual work I did on this battery, which was for a MacBook from like 2007 or 8 or something. It's pretty old. But they all have the same issues. It's just the details might be a little different for each chip. So anyway, this is a battery that you can find in the bottom of an old MacBook. So there's little screws on the side. So you take those apart. And then you can just like rip off the plastic part. And you can start to get inside more. Okay, and then what you see on the inside is 3 lithium polymer cells, 3, and then they're actually 2 deep, so there's 6 altogether. And then this part on the end is the actual electronics, so the chips and stuff. So then you can rip that off, and then you can start to see the various chips. All right, so then the electronics piece actually unfolds into like 2 separate boards, and so then you can start to identify the actual chips based on writings that are on it. So here you see a chip called BQ29312, and that's from Texas Instruments. And so you can look up the data sheet for that guy, and so it's what they call an analog front end battery protection. So it's supposed to be protect. It's a safety mechanism. So it provides safety protection for overcharging, overloading, short circuits, overvoltage, so all the bad things, right? And it's not on, I haven't really talked about SM bus is yet, but that's basically the channel that lets the OS talk to the battery. So the OS can't talk direct, or the charger can't talk directly to this chip. But what it can do is it talks to the main chip, which is this BQ20Z80, and it can tell that chip to talk to this chip. Okay, and then so these pictures are, Travis Goodspeed gave me these, and he's just like Mr. Hardware. It's like the opposite of me. So I didn't even ask him, he was just curious. Like when he saw my talk coming up, so like last week, he found a battery, he ripped out the chips, he put them in an acid bath and x-rayed them and did all sorts of the magic that he does. So this is what the chip looks like on the left, and on the right is a zoomed in version where you can actually see the logo and all that stuff. So it's pretty cool. Okay, so then you flip the board over, you can see the other 2 chips that are important. So one is the main guy, BQ20Z80, so that's the big chip. And then there's another smaller one called BQ29412. So start with the small guy first. So again, this is, so you saw, if you were paying attention in those data sheets, so it said first level protection. Those were the values that are communicated to that other chip we just saw. And then there were some other ones that said second level protection, and those are the values that are communicated to this little chip. So this one, all it does is provide overcharge protection. And again, you can't talk directly to it, but you can talk to the main chip, who will then communicate to this chip for you. And then so here's the main chip, BQ20Z80. So it's what they call SBS, so Smart Battery Specification Compliant Gas Gauge. So this threw me off for a while when I was a gas gauge, I think about my car or something. But that's what they call it because it measures, power. So it's like the main brain. So its job is to measure, how much charge is in the battery, keep track of that, figure out how how long it will take to discharge, that sort of stuff. And this is the thing that you can talk directly to. You don't need wires, you don't need to mess with it in hardware. You can just, while the computer is running, you can communicate with this chip from the OS. All right, and again, here is the X-rays and after everything's been cleaned. So this is the main chip, the BQ20Z80, and then you can see the logos that were in there. If you look real closer in the corner, so there's like a Texas Instruments one, and there's this one from BQ, which is, I guess, a company that Texas Instruments bought at some point. So thanks, Mr. Goodspeed, for these photos. They're pretty cool. Okay, so now I already kind of knew what chip it was, and then I finally tore it apart, and I was like, oh, look, I could have torn it apart in like 2 minutes and figured out what chip it was just by like reading the inscription on the chip. But I did it the hard way. But another clue I could have had was in one of the header files that I already had. It's like BQ20Z90 and chipset reference manual, blah 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 blah. So I didn't notice that. But that's part of the fun of doing the research. Okay. So where are we now in the story? So I know what sort of hardware there is. I know the chips that are involved. I can download data sheets and learn about what they do and how they work. I've seen in the upgrade mechanism how you can, at least on the first level, how you can talk to the chip. And so I just need to learn more about how it works and how to talk to it, and then maybe I can get somewhere. Okay, so then I finally was actually reading the smart battery specification, and this is basically how your computer charges batteries. So there's 3 important parts. So there's the smart battery, which we've already kind of talked about. That's the guy in the middle there. Then there's the charger. This is the actual device that sends the charge to the battery. And then there's the host, and the host is like your computer or whatever. So this is the one that supplies it's the reason for the battery, right? So you can see exactly how everything works in this chart, and I'll talk a little bit more about this chart in a second. So if you notice on this chart on the bottom it says SM bus. So this is and I mentioned this a few times already. This is the way that you can the actual protocol that's used to communicate to the battery. So SM bus stands for System Management Bus. It's based on 2-wire I2C, so there's 2 wires. And you can check out Stephen Ridley's talk that he gave at SummerCon, and he talks all about I2C. And there's lots of devices in the hardware world that talk I2C. And then there's this smart battery specification document that explains how this all works. Okay, so the system host. So this was the thing on the left in that diagram. So that's basically your laptop. So its job is to find out information about the battery and report that to the user. So like, hey, how hot are you? How much voltage do you have? How much longer are you going to be able to have a charge? Should I go to sleep because you're about out of charge? That sort of stuff. And then when something critical happens to the battery, like it's about to run out of charge, or maybe something like really critical happens, it gets too hot, it can report that to the battery. To the host. Okay, so then the charger is again the thing that is actually supplying the current to the battery. So it can communicate with the battery. And so this is sort of like, it may, to show how little I know about how batteries work before I did this, I was like, it's really weird that I can charge my battery with my computer off, right? Because shouldn't the OS have to be involved? But it turns out that no, because the charger can talk to the battery without the OS even being involved. And that's why you can charge your battery when your computer's not plugged in. So the whole point is the charger changes how much current it delivers based on what the battery tells it. So there's 2 kinds of chargers. There's one called a level 2 charger, and these are like sort of the dumber of the chargers. So here, the smart battery just gives it data, it gives it information, and the charger just does whatever it says. So like, it's the battery's job to report to the charger in that case. And then the level 3 one's a little smarter. So here, that's wrong. It should say smart, or the charger or whatever. So the charger then actually, the level 3 one, the charger talks to the battery and asks it questions and decides. So it's less of a passive role there. And if you read you can communicate over SM bus to the charger on the MacBooks too, and you can ask it, one of the things you can ask it is, what level charger are you? And it reports it's a level 2 charger, which is the dumb one. But if you watch what it does, it actually acts like a level 3, so who knows? So I can actually see, you see, later on I'll show you how to like sniff the information. You can actually see the charger talking to the battery. So and then finally, you know, the smart battery is, its job is to, you know, to make sure that it knows what's going on inside itself. So how much charge it has, what chemistry it has, all that sort of stuff. And of course, it has to make sure that nothing bad happens to it. Okay, so that's the battery. What about, you know, so what's this stuff about how does the computer talk to it? So I already mentioned that there's this Apple Smart Battery Manager kernel module that does it for the firmware update at least. And so we can actually use that to talk to the battery. So the way you use it is you can just see exactly how it was used in the firmware update. So you open up an I/O service, and then you start using this I/O connect method, structure is 0 function. But you don't have like raw access to it. You can just write with well-defined SM bus communication, which is fine for what we want to do. We're not like trying to fuzz the battery or something. We just want to talk to it. And then so you don't have to use this big complicated function. I wrote this API that I'm releasing at the end of today that allows you to very easily talk to the battery and get values back and stuff. All right, so I don't know if you can read this very well, but so this is an example of how you use that big complicated function to talk. So here I'm trying to read a word from the battery. So I say things like, I basically am just setting up. So there's this input. It has a type, read word, and then an address. Address is like the command, right? So remember there's going to be a lot of different commands for SBS. And then I call this big complicated IO connect method structure, blah, blah, blah. And then it reads it, and then I get the output, and I return it. So the good news is like this is kind of complicated, but now there's this read word function you can use that you just give it an address or command, and it just reads it, and it's done. So it's easier. So here's examples of using the API that I provide. So like now, instead of reading, you know, that going through their complicated way, to read a word, to read the serial number, for example, all you have to do is say read word serial number, and it returns it to you. And then unseal. So remember, unseal is to get access to it. So it allows you to make changes to the battery. So to do that, you just unseal and you give it the password, right, which we know. And then you can write words. You can write blocks. So that's basically the only three things you can do is you can read and write a byte, you can read and write a word, or you can read and write a block. And a block is just, you know, however much data you want. So here is 7. So I'm writing the device name. And then if you want to read the data flash, remember I talked about there's these subclass IDs and stuff. And so if you want to read the data flash, you have to do it in 2 steps. First, you write a word to tell them which data you want to read. So in this case, 57 is the one I care about. And then you read a block from, and then you get the data back. And then again, if you want to get full access, which is even more power, more control over the battery, you can just say get full access, give it the password, which is all Fs for all Apple batteries. And then when you're done, you can seal it back up. So using the API, you can like muck with the battery pretty easy. Okay, so what, I mentioned there's these different commands and stuff. So what are some of the commands you get? So there's this document you can get from Texas Instruments that explains all the different commands that this particular chip will accept. And it outlines exactly the 3 chips that we have. So you can read down these and see there's lots of different things you might be interested in. So you can get the temperature, the voltage, the current, cycle count. So this is the thing that lets Apple know how many times you charge your battery. So you just set that like 10 if you want. Chemistry, device name, and then so you see the first column is what they call standard commands. And I'll talk about what that means. And then the next column is extended commands. So you get sort of the more complicated things. So you can like change your password. You can read the data flash, that sort of stuff. And then on the bottom right is all the different data flash that you can get to. So first level, second level, safety things, and all sorts of other information. Okay, so at this point we can make changes to this, right? So like maybe just by making changes to it, we can cause a problem, right? If you say like, hey, things aren't bad at 4,000, milliamps or something. It's only bad when it gets to 6,000. So when you get to 4,000 or 5,000, you're still okay. Right? So maybe by changing these safety thresholds, you'll cause a problem. So you can see some of the things you can already change. So and some of them are like very complicated. So like there's these impedance tables and temperature models. These are things that like only people who work at Texas Instruments really understand, but we can still change them. Overvolt thresholds, each for each cell, for the entire pack. All this kind of stuff we can start messing with at this point. So I did, right? So I started changing some of these values, and nothing like that interesting happened. So the reason is like I can change where all the safety values are to make them much higher than they should be, but the thing still knows like when to turn off, right? Because I didn't change the charging algorithm. I didn't change the way it's reporting to the charger. All I changed was if things start to go wrong, it's not going to freak out. But things didn't go wrong, so I needed to dig deeper. So you can see in my dig dug picture. So there's unseal, which I've talked about, and then there's full access, which is a little lower, and then there's a level that's even lower called boot ROM, and that's really where like the really cool stuff is. I haven't mentioned that yet. All right. And so before I talk more about the different levels, I just want to take a little digression into the chemistry because this is something I thought was kind of cool that I found out. So I mentioned that these batteries you should be able to plug in. No matter what kind of chemistry they have, it should work. So it'd be kind of cool to know, to just tell it you had a different chemistry and how that would work. So it turns out that, I don't really know how that works, but, and it's not documented anywhere. This is one of the things that only, the factory should be messing with. But you can actually get to it. So this is sort of a sneak peek at something I haven't actually talked about yet, but there's this evaluation kit that I'm going to talk about in a minute. But the evaluation kit can actually change the battery chemistry. And so you can watch and see exactly how the battery chemistry is changed, and then you can figure out what parts are important as far. You don't necessarily know what they mean, but you know at least which parts have to do with the chemistry. So if you sniff the traffic going to the battery, and I'll talk about how you do that in a second, while you're changing the chemistry, you see that there's it's doing these kinds of writes. So 52 bytes, it writes to this data flash subclass 83, and then 50 bytes 84, 20 bytes 85, and so on. And then there's 20. So and those aren't documented anywhere what those are. So the document that describes the chip, it acts like there's no such thing as subclass 83, but obviously there is. And then there's these other things, these cell impedance tables. It changes those, and then it changes these impedance track parameters. And what that is what Texas Instruments, their patented algorithm on how to figure out how much charge you have. And so most of those values, I have no idea what they are. But one that I did at least figure out what it was supposed to be was subclass 83. So there it starts with a chemistry ID, which you can see what that was from the little, the GUI that I was using. And then it was a bunch of unsigned shorts. And so if you pull those out and graph them, you get this little graph whose value has to do, is very close to the numbers you see in voltage. So it's some sort of voltage graph, right? And so you can change that graph to look however you want, and that will represent some sort of way you charge a different kind of chemistry, and so that could cause some interesting stuff maybe. Okay, so now that I found that changing the chemistry has to do with these undocumented subclass IDs, it's like, well, I wonder what other ones are undocumented that they don't talk about. So I just tried to read every subclass ID, and then I compared it to the documentation to see which ones aren't listed, which ones do they not talk about. It turns around there's 6. There's 6 of them that aren't documented. So there is 57, 65, 66. Those are both 10, relatively short. And then there's the 3 that have to do with chemistry. So and at the end you'll see at least what one of those other 3 are. So again, basically all the ones that are undocumented are actually really important, not surprisingly. Okay, so let's talk about the different modes in the battery, and we'll see how, and since we have the full access key, we can actually access all these modes. And I think that the deeper you go, sort of the more havoc you can cause. Okay, so when it leaves the factory, it's in sealed state. And so that means you can't do anything to it. It's the way that all of your guys' batteries are on your laptop right now. So you can only query it for information, and you can only query you remember how there was the 2 columns? There was the standard ones, and then there was the extended ones. So you can't talk to the extended ones. You can only talk to the standard commands. And you can only read them. You can't write to them. So it's, it's just the most basic access. You can't change anything. But if you have the unsealed password, which we do, then you can move on to the unsealed mode. So in the unsealed mode, then you can access some of the extended commands. You can access the data flash now, so read and write. You can access some of the standard commands you can read and write too. And then this is the mode that the firmware updaters entered. So this is what I saw when I reverse engineered the firmware update. The next one up is the full access mode, which again, we know that password because it's the default. So now you have access to all the SBS commands. Anyone that has write abilities, you can write to it. And you can enter these other two modes called boot ROM and configuration. And none of the firmware updates I looked at had to enter this mode. This mode is like for serious hardcore changes to the battery. So the configuration mode, there's not really any documentation on how that works, and I never saw anything that entered this mode, so I only know from this one document that sort of offhandedly mentioned what it does. But what it does is basically, the battery has little sensors that figure out, that it thinks it knows how much current it's seeing and how much voltage it has, but maybe these little internal sensors aren't working very well. And so you give it a set amount of current, and you tell it how much temperature it is, and then it can adjust the way it's working based on what you tell it, right? So maybe it thought it was getting, 300 volts, but really you were giving it 312, and so you tell it that, and then it can adjust its internal sensors and stuff. And so the way you do it, is these commands here using the API I talk about. So you tell it how many cells there are, the current, the voltage, and the temperature, and you say calibrate to those, and it'll calibrate. So I was like, well, those things are cool, right? So current, voltage, and temperature, it'd be nice to totally confuse it on how much of those it's getting. I wonder if there's any other things that you could get. And so something I like to do when I'm confused is ask the vendor, right? So I went onto the Texas Instruments site, and I asked. I said, hey, can you change other things? And then this person, Jackie, who works at Texas Instruments, she responds, and she's really nice whenever she responds. And you'll see some of the other people aren't as nice. So she says, no, only current, temperature, and voltage. And the only reason I bring this up is I think it's really cool how I'm a prodigy. If you see, I have 105 points in their system. I don't know what that means, but I like to be a battery prodigy. And someone just the other day on Twitter was talking about they found me in 2007 posting something asking about cross compilers for iPhones or something. This was back before there was even jailbreaks or anything. So if you just stalk me, you can see what I'm working on because I just post questions everywhere. Okay, so that was configuration mode. There's the mode that's really important is called boot ROM mode, and so this gives you low-level access to the thing. So it lets you. So once you're in this mode, you're not talking SBS anymore. You're talking to the hardware. So you can access direct access to the data, direct access to the instructions, everything. And the document that talks about how to talk SBS doesn't talk about this at all, because you're not really supposed to do it. So I had to go and buy some more hardware. I haven't had to buy too much hardware yet, but pretty soon I'm going to start to have to buy a bunch of hardware because I'm going to start breaking stuff on accident. So the thing I bought was this evaluation kit from Texas Instruments. And so it comes with this green thing on the upper right here. This is basically the electronics from the battery, the little board that's electronics, except it's bigger, so you can see the chips easier and mess with them. And then it's got a device that lets you talk to it over USB from a Windows GUI. So it's kind of cool.
Charlie, how much did that cost?
I don't know, a couple $100 or something. So it's cheap when you're using the company credit card. Yeah. So this is what it looked like at my house. So you have to hook up. I ripped some cells out of a battery and plugged them all in, and this is what it is. And then if you see in the upper left, actually, there's something I got from Radio Shack, and I would go into Radio Shack and ask them about batteries and how they worked and how you could overcharge them and stuff. And those guys weren't helpful at all. They didn't know what I was talking about. Anyway, so this is what it looks like, and then there's a cable that runs to your computer over USB, and it allows you to talk to the chip. And so this is really useful. And then someone was asking what that little guy is at the beginning of this slide. So this is their little, Clippy, their battery guy for Texas Instruments is this little dude, and so I liked him. So this is what the software looks like when you run it on Windows. And this is what the screen looks like. So this allows you to do things like, talk SPS. So you can change values, you can read values. The things on the bottom are like, bit fields, and breaks out the bit fields for you. That's sort of nice. Teaches you how to do things. And then here you can press the data flash button. And so here's all the data flash values. You can read them or write them or whatever. And then, of course, I was like immediately like, pro mode. Yeah, I want that. So I press that. It says, like, this system is only for advanced users. And obviously, if I'm a prodigy, I'm allowed to do that. So you can do things like do raw reads and writes over SPS, which is cool. And then the really interesting thing is you can flash the thing. So this is something I want to know how to do, is flash the device, because I want to change the firmware. So the evaluation module comes with like 1 or 2 different firmware files, and they're in what they call SREC files. And so the idea was, okay, well, I'll sniff over USB what it's doing when it programs it, and then I'll know how to program it on the Mac by just talking to my API. So what are these SREC files? So SREC files are what Texas Instruments says are encrypted firmware files. And so if you break out the way that it decrypts it, it's like XOR. It's to give them some credit, it's not just like XOR 1 byte. It's like XOR a byte and the previous byte. So it's sort of like iterative. It's pretty fancy, but it's still just XOR. So anyway, so you can take one of these SREC files, and then you can see what's in it, and there's some like header stuff, and then there's the full data flash and the full instruction flash, and then some checksums. Okay, cool. So then what I did was I wrote a PyDebug script to sniff the USB, and then I could see exactly how the programming worked. I could see when I said to program a raw, write 4 bytes or whatever, I could see how that was, and so to make sure I was doing it right and all that sort of stuff. So I just sniffed it, and I watched it program it. So I made sure that when it's on the boot ROM level, this is when you want to read a word, you have to send command 8, right, command 4, and so on. So I'm basically reverse engineering the protocol at this point for boot ROM, because I don't know how it works. So then I'm like, well, now that I know a little about it, let's go back to Google. So I Google for SMBus, boot ROM, read 8, write 4, which is basically all I know. And it pulls up this document that talks about the ROM API. And that's exactly what I need. This exactly tells you how to write, how to communicate to the battery when it's in boot ROM mode. So awesome. And it also talks about the layout of the firmware a little bit, which is also good. So if you sniff how it programs it, it does exactly this. So it does a mass erase, so that erases all the instructions, and then it erases every row of data flash, and then it starts to program the data flash 1 row at a time, and then it does a checksum, and then it does the instruction flash 1 row at a time, and then it does checksum. Cool. So now maybe I could do that. So I sort of understand now how I could flash the thing if I wanted to. I could probably figure out how to read from it, just by, I've never seen it though, but now that I have the document, I could probably do it. But I should warn you that when you're in boot ROM mode, it's very easy to brick the thing. And so now I can get all the data flash probably by the same thing. And the most important thing I need to know at this point is what sort of, so I get the firmware fine, but I don't know what kind of chip it is. I don't know, what it means. I can't disassemble it. So that's the first thing I need to do. And so reading the flash looks like this, so it's pretty straightforward. I'm just going to skip it. So reading the data flash, again, it's just APIs. It says it loops through for the 40 rows, and it does a row. It reads the row. It's pretty simple once you know how to do it. So what I really want to do, though, is disassemble the firmware and see what the hell it does. So the first thing I did was I just tried every single one in IdaPro and hoped for the best. And none of them worked, not surprisingly. So then I did what I always do, is I asked Texas Instruments. So I said, hey, what kind of processor is executing the code that you give in the senc file? Is it like ARM or something? I don't know. And so the guy writes back, proprietary. See? I really needed Jackie to answer my question, because she would have probably told me. And so then I'm like, well, I'm just going to kill this guy, Doug Williams, with kindness. Hi, thank you so much for your response. You know, so do you mean like you're not going to tell me because it's proprietary, or do you mean like it's some chip that you made in your basement and no one knows about it? Thank you. So he says it's the first. So they have customers, Apple probably, who create custom firmware, but they don't talk about the details. They won't tell me. So that wasn't fun. And he's an expert. He's not a prodigy. But, you know. Yeah, well, I don't think he would have bought it. So I like how he says he's going to protect his intellectual property. And so I'm like, well, I'm going to take your intellectual property. So I have the firmware. And so now all I can do is look at the raw bytes and hope for the best. So what pops out, right? At first I was like, this is hopeless, right? But it turns out there's like some clues if you start to look. So I'm like, hey, there's some threes and stuff, right? That sort of sticks out. What else? It's like random crap in threes. So what else do I see? Oh, there's the threes, in case you hadn't noticed that yourself. Okay, so then I said, well, and actually DM Lozakis helped with this too. So there's these threes, but they only show up every third spot, right? So maybe there's something significant about, you know, three bytes or something. So maybe it's that the instructions are, you know, 3 bytes or something. But then you start to notice this, like if you align them on you know, cuts of 3, that this one line, it's always 0, 1, 2, or 3. Right? So that's like, well, okay, the high nibble is always 0, 1, 2, or 3. So maybe it's not 3 bytes instructions, it's 22-bit words, right? And so now I'm starting to like, okay, maybe this is something I can figure out now. So here's another one with 0, 1, 2, or 3. So I'm getting some clues into what it is. And I didn't need Doug Williams or whatever his name was to tell me. And then if you look at the very bottom of the firmware, there's some more interesting stuff. So it ends with 23FFFF, and then there's a bunch of 3FFFFFs. So there's the 23, and 3F. So like, you know, that makes me think like, you know, that 23FFFF might be something important, right? So any guesses on what the last instruction in firmware might be? I think I heard it. So what if it's a return, right? That's how I would end a function. So I looked for 23FFFF throughout the firmware, and sure enough, I see it sort of scattered about, which is what you would expect to see with returns, right? So I'm pretty thinking like, yeah, maybe that's a return, and then, you know, I don't know what the 3FFFs are. Any ideas what that is? What would you put after the very last function? No ops. Okay, so anyway, so then back to Google. Dion came up with this Google search. I can't take credit for it. His Google foo was stronger than mine. So you Google for 23FFFF, 3FFFF, 22-bit, and then you start to figure out what it is. So there's this document called AppNote 60 that talks about what kind of, so it says actually, if you look closely here, it says right here, so like 3FFFF is a no-op. Oh yeah, that makes sense. That's what I would put at the end if I didn't have anything to put. And then it says 23FFFF is a return, which is what we kind of thought. So this is probably it. So then inside there, they tell you it's something about a cool risk. So you Google cool risk, and you get a document. And it turns out that as far as you can tell, that this thing runs cool risk C816. So now I know exactly, and there's a great document that tells you exactly what the instructions look like. So now I can reverse engineer the firmware on the battery. So stuff about cool risk 816 is it's 8-bit, so we already kind of knew that. It's got Harvard RISC-like architecture, and we've kind of seen that too, right? There's this data flash, and then there's the instruction flash. So there's these two separate things. 64K for the data, and 64,000 22-bit instructions is what it has. And then you've got 8-bit registers, and of course, Ida Pro can't do it. And the best line Angelina Jolie ever spoke in a movie is about RISC architecture. Everyone knows that. Okay, so what do the registers on this thing look like? So again, we already mentioned they're 8 bits. Some of them can kind of combine into some bigger ones. So it's same old stuff. And then you get these sort of weird addressing modes. So you can so move R0 in parentheses and so forth. So you can figure it out. But basically, you can sort of pre-increment or post-increment and that sort of stuff. And so luckily, since it's RISC, there's not that many instructions. So there's like, I don't know how many, there are 30 or 40 instructions. And so all I had to do was teach IDAPRO what those were, and then I could pop it into IDAPRO and see how it worked. So there's this, part of the document tells you exactly how to interpret bits and what instructions they are. So I just had to write an IDAPRO processor script in Python that interprets exactly what those are and for IDAPRO. So then once you do that, which is a lot of work, and trying to debug that is really difficult, like debugging something that's, disassembling something in IDAPRO, it's a pain. But I got it mostly working. And so then you can just pop in IDAPRO, your firmware, and now you can select BQ20Z80, and I'm gonna release this stuff if you want to play with it. And then you just have to set up a spot for the data flash, and then a spot for the instruction flash, and you hit go, and then you're good to go. So the first time I did it, I was like, oh crap, IDAPRO didn't do a very good job, even with my super awesome processor script. But I know that basically everything's 3-byte aligned and everything's an instruction. So let's just, because of the whole RISC architecture, so let's just tell it, I wrote another script that just goes through and disassembles every 3rd byte. And then IDAPRO, much better. So then it disassembled basically the whole thing. And the 2 little regions at the end it didn't do are a part that I'll talk about in a minute. All right, so then you can start to see how it processes the SBS command. So like remember, the OS asks it SBS command questions, and then it responds. And so here you can see examples of, number 21 is device name, and so it exactly is doing for the device name there. And then likewise for the manufacturer name. Okay, so now I can disassemble the thing. I can disassemble the data flash. I've seen how you can flash the whole device. But now is when I start to use the company Amex to its full extent. So it turns out when I start messing with it, the devices stop working, right? So and part of the problem was I noticed that when I dumped the firmware from the battery, they're not identical when you would expect them to be. So probably I'm doing something wrong. And then when I make changes to it, it's bricked. It doesn't work anymore. And if I try to flash the whole device and copy exactly what the evaluation module does, it bricks it too. So I'm sort of stuck. And you can see that it sort of sucks. These batteries are expensive. They're like $130. And I was ordering like 2 or 3 of these at a whack because I was going through them so fast. And so here's like a pile of batteries that don't work anymore at my house. There's actually more than that. This was an early picture. So I was like, well, I can't afford $130 every time I screw up because I screw up a lot. So I'm going to go for one of these like off-market brands because they're only $40, right? I can afford that. So I ordered one of those, and they changed the unseal password. I couldn't hack it. So it didn't do me any good. So I had to go back to Apple to get theirs since they didn't secure theirs. Okay, so the first thing I realized was that when I was reading when I was dumping the firmware, when I was doing reads, sometimes the reads weren't giving me reliable data, but it didn't like error out or anything. So I changed my code to read a couple times and make sure I always got the same thing, and then things were good. So now when I read the firmware twice in a row, they agree. And the reason that this says hotel is because I was using like the military alphabet. So you can see I was all the way up to the letter H by the time I figured this out. So that was a lot of money in batteries. Okay, so now I take the MD5 sum. They agree, yes. And then I dump the data flash and do a diff, and they mostly agree. And that's not too surprising that they're not perfectly the same because some of the things that are changing are like the number of times you've popped into boot round mode. Okay, so then this was my life, was this little X on the battery. Every time I screwed up, I'd be like, oh, the X. Because that meant you were screwed. So then I noticed something else. I would make changes to the firmware. So then at this point, I could dump the firmware. I could write to it. But then when I started to patch the firmware to do like other things that it was supposed to do, that's when the X would show up. And so then I was like, what's going on? How does the computer know that there's something wrong with my battery? And so I looked and I watched what it was doing, and it was doing this data flash failure flag was set. And so I read in the document, and it's like, blah, 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 and then it says like, after full reset, the instruction flash checksum does not verify. Oh man, there's a checksum. At least it's not a signature, so maybe I can figure it out. So I got to somehow figure out this checksum and fix it, or else it doesn't let me change the firmware, which isn't any good. So remember I mentioned there's these two little sections at the end of the IDA that it didn't disassemble. That's because these are actually function pointers into some ROM code that you can't mess with, and it's documented in that boot ROM API what each of these are, and one of them computes the flash checksum, which is exactly what I'm interested in. So I found where that was, and in IDAPRO there's only two references to it. So one is to a function I hadn't looked at yet, and one was to one of the SBS commands that aren't documented. But I did see somewhere on some forum somewhere someone said that it was supposed to return the checksum. That makes sense. It doesn't return the checksum for me, but so I looked at this other function that I had never looked at before, and you can look at it and see exactly what's going on. So the first thing it does is it loads up an address from data flash, in this case 4214, and then it adds a little offset to it and it dereferences that value. And then if that value is 0, it just skips to the end of the function. And if it's not 0, then it reverses the like endianness of it. And then it calls flash checksum, so it gets the real checksum, and then it starts to compare byte for byte, the real checksum versus this value that was stored. So obviously the stored value here is the checksum. I don't know what the checksumming algorithm is though, but I do know that if I set it to 0, it doesn't even bother. So all I have to do is set this value to 0, and then it won't ever check the checksum again, which is pretty awesome. So this is the old version of the firmware, and then there's some newer versions of the firmware had something different, probably because like zeros you just might stumble upon. But so they put it in this little like encoding scheme for the saved checksum. You can see what this is, but basically it's not real complicated, and again it decodes the thing that's there and it compares it to 0. If it's 0, it just keeps on going. So if I want to make changes to the firmware, all I have to do is, on older versions of the firmware, set it to all zeros, this value in data flash memory. And if I want to do it on the newer ones, I just have to set it to the encoded 0, which turns out to be 0, 3F, F7, FF. And then there's maybe some other ways to do it. But the bad thing is that you have to do this in boot ROM to get raw access to the data flash, which I'm scared to go in boot ROM because I always torch my batteries. So it turns out there's a way you can do it without going to boot ROM, which is much nicer. So if you can just dump all the data flash once, then you can, if you call each of the SBS commands to read the data flash, you can figure out exactly which addresses you get for each data flash command. And so you can actually find where the checksum is stored. And it's actually returned by one of the SBS commands. And it's one of the undocumented ones. See, I told you the undocumented ones were cool. So the undocumented subclass 57, if you return that, it gives you the checksum, and you can write the new checksum and write it, and then you're done. So here's the little bit of code that will, without going to boot ROM mode, will disable the checksum on the device. All right, so now I can make arbitrary changes to the firmware that's running on the battery. So, and I have this function called patch firmware that'll do it. So here's an example of using it. So here I'm changing, I go to offset 73611, which is like the very, very end of the firmware. And I want to change it to 123, or 122. So then I see that it works by dumping the firmware again, doing a diff, and sure enough, I changed the no op to 122. So now I can change it. The checksum's cool. I can do whatever I want. But now what do I want to do? So here's where I'm at, right? This is like almost the end of the talk. So I can make arbitrary changes to the SBS parameters. I could do that a long time ago, right? I can make arbitrary changes to the data flash. I can make arbitrary changes to the instruction flash. So I can make the battery report or act in whatever way I want. And the main thing I don't understand yet is how does the charger and the battery really communicate? So I need to like confuse the charger now, right? I want the charger to charge me a lot if I want something bad to happen. So then I figured let's actually sniff the wire that the communication is going on, and then I'll know. So I bought some more hardware stuff, and I wanted to figure out how to sniff it. And Stephen Ridley helped me with this a lot. So if you look at the battery adapter, there's like 6 little slots, and then there's actually a couple more little wires there. So 2 of those probably are SM bus. I just had to figure out which 2. So the first thing I did was try to connect all these wires to each other, right? This was really a disaster. So somehow when I was doing this, I short-circuited my motherboard. And I had to take it into to the Apple Care guys or whatever, the Genius Bar. And they're like, what happened? I was like, I don't know. I just turned it on and it wasn't working anymore. So I got fixed. So then they really should like put my picture up because I'm always going in there with these wacky stories. And the next thing I was like, well, those like removable wires, that's not cutting it. I got to like make a wire. So I got out the soldering gun, and this is like really unlike me, like because I'm a software guy. So I built this like crazy wire, tried that. No, it didn't work. So what I finally figured out to do is like just take off the keyboard, and then the battery's sitting there where it's supposed to be sitting there, and then you can but the wires are exposed, so you can just still put little probes on it. So that was the right way to do it. And the worst thing is this cable, I literally took like 4 days to build this cable. So Travis could have probably done it in like an hour. So once I did that, I put it into the logic analyzer here, and sure enough, I can see which of the channels is talking. And it actually has I2C built into it. So you can see, it's already telling me that it's like writes and stuff, and I'll zoom in a little bit to show you what it looks like. So just looking at the traffic, you can see the SBS stuff going on. So it's a write to 8. You can look up 8. 8 is temperature. And the response is B73, which in decimal is 2931, which is in Kelvin. And so you can convert that to temperature, Fahrenheit, so 67. That makes sense. And then again, you can get the charging current. You can see it's a write to 14 and a read of D48. So this is cool. The problem is if I want to run it for a long time and see what's going on, like this, I don't want to be like taking notes off of this tool. So I got this other thing called the Beagle sniffer, which is like really cool. So here's how you hook it up. The thing it took me a while to figure out was you have to actually plug the grounds onto something, otherwise it doesn't work. So then you get a GUI that looks like this, and so you can see again it's a write of 16, a read of 80, a write of 8, a read of OB87, all that stuff. All right, so then I sniffed for an hour and watched what it did with the laptop off. So this is only the charger talking to the battery. And so I see it only queries these few things: battery status, temperature, charging current, voltage, battery mode, relative state of charge, main capacity, and full charge capacity. So these are the only things the charger ever asks the battery. And the only ones that ever actually change while it's charging are the temperature, makes sense, the amount of current that's being delivered, the voltage that it has saved up, the relative state of charge, which is like 20%. It's a number between 1 and 100, or 0 and 100. And the remaining capacity, so how much it has left. So these are the only things the charger cares about. So my idea was, well, why don't I have the firmware lie about these values? See what happens. Here's a graph of those values over time. So not surprisingly, the voltage goes up, the amount of current goes down, eventually to 0. Okay, so here's basically the end. So I can do whatever I want to the battery, and I'm not sure what that lets me do. So I can clearly brick the battery. That's a cinch. I'm a pro at that. And then I can make the battery firmware lie to the charger and the OS. And then you could, in theory, attack the OS from the firmware, although I didn't really do that. So here's an example if you want to brick it. So if you want to brick someone's battery, here's code that'll do it. So all you do is do a mass erase of data flash, and then run back into, tell it to seal itself up again, and then you're screwed. And then the really mean thing is, like, you could do that and ruin their battery, and then when they put in a new one, you could do it again. But I wouldn't do that. So what about these firmware changes? So it'd be cool to change those, and that's what I did. So the things I changed are things like remaining current, full charge capacity, voltage, and these are all SPS commands that happen to be between 3 and 16. And there's one function that actually handles that. And it looks like this. It's just a big switch with cases and stuff for each one. So you can see, like, compare to F, compare to 17 or whatever. It's a nice little graph. So this is in the firmware of the battery. So I want to make changes. So I'm going to say, well, instead of when you ask for remaining capacity, I'm going to tell you manufacturer date. And when you ask for full charge capacity, I'm going to tell you the serial number. And the reason I'm going to do that is because the manufacturer date and the serial number are both things I can write to. They're both words, which is the same thing that remaining capacity and full charge capacity are. And they're never queried by anybody, so no one cares that I'd change them. So I can set them to whatever values I want. And then the charger will think that the remaining capacity is something that it's not. And then it might overcharge it. So this is what the firmware looks like for F to 10, which is the two things I want to change. So then I can just start patching it, like you would expect. And so to patch it here, all I do is I add to the value that they're switching on, and then I jump to the case that I wanted to jump to. And so the result is I ask it what the remaining capacity is, and coincidentally, it's exactly the same as the manufacture date. And same thing for full charge capacity. So then I can do the same exact game for changing the relative state of charge to be the time remaining. So I can do this to all the values, and I did. So this one's a little more complicated because before, the case statement was only for the exact two I wanted to change. Now it's like it's a big case statement for everything between 5 and F, but I only want to really change one of the values. So I have to sort of compare and then jump and do some more coding. And I can reuse that extra space that I made from the last bit. So here's what the patch looks like. Kind of going fast now. And this is what it looks like after. So this is before, this is after. So now it compares to 9, which is another value I want to change, goes off and does something different. Compares to D, which is the one I really want to change, goes off and does something different. The rest, it does what it was supposed to do before. All right, so now what happened? So I changed that. I made it all constant values, so no matter how much charge you deliver, I'm at 50%, I need more charge. So what did I see? So I can set all the things to arbitrary values, whatever. I can change them on the fly, right? Since I can just write to, say, manufacture date anytime I want. So I can change it like every second. I can make it go up or whatever I want. But when I do this, I didn't actually blow up the battery, of course. But what I did notice is I do have effect on the amount of charge that's delivered. It's not like an easy out, like I do this and it does that, but it definitely changes. I just, the algorithm is not super easy, though, how it does it. The one thing that might save the day is there's these thermal cutoffs on the batteries. So these are little, chemical fuses that when things get too hot, the little chemicals melt down and then you can't charge it anymore. And so that might be the saving grace for this. I don't know. I never had it even get that bad. The interesting thing is, while the off-market battery was cheap and it was sealed, it actually didn't have these fuses. So that's probably dangerous. Again, the OS kernel, if you had a bug, you could attack the OS from the battery. To find such a thing, you might want to fuzz the little bit of the kernel that talks to the battery. So I imagine a couple ways you could do that. You could write your fuzzer in cool RISC assembly. That would be insane. And then the other thing you could do is you could just actually hook wires onto your, this communication between the battery, and you can just push SM bus commands to the OS that way. So that'd be kind of cool. But I didn't do that. And then the one thing that like I said, I never blew up a battery. I'm not real worried about someone blowing up mine. I'm not too worried about someone bricking mine. But if you are, I have this tool that you can download. And what it does is it just changes the password for the full access. If you're really paranoid, you could change the unseal password too. But I didn't. So what this does is it changes the full access password to something random. No one knows it anymore. No one can get it. The bad thing is you can't reverse it. So if you change your mind, it's too late. You don't know the password anymore. And if Apple ever released a firmware update, then it would not work if it needed full access mode. So those are the bad things. And the thing that's really bad is, A, I wrote it, and B, I've only run it on one computer ever, this one. But it works great on this computer. So keep that in mind. So you can download that. I have the source code in the binary. You can just run it once. And basically, it's not brain surgery. You just change the password. Okay, so the slides, I have a white paper that has a lot more details about all this stuff. And the tools, like the caulk gun, and I have the firmware dump, I have IDB files, I have processor scripts, everything is all available at this URL. So feel free to download that, ask questions. Thanks to all these guys who helped me out at various points in the talk. That's it. Thanks.